This is the beginning of the Chapter 14 homework for Physics 102B. Starting with number 27, it says find the internal energy change when 1.25 moles of helium gas is warmed by 100 Celsius degrees. So here we have, first of all, that it's a monatomic gas. We have N equals 1.25 moles. Change in temperature is 100 Celsius degrees, or you could call that 100 Kelvin. So if we want to know the change in internal energy, that means we're looking for delta U. And we remember that delta U is 3/2 nR delta T. So we just plug in the numbers. 3/2 N is 1.25 moles times 8.314 times 100 Kelvin, and that gives an answer of 1559 joules. Number 31. Number 31 deals with krypton, which is a monatomic gas. Sorry about that. Alright, krypton. A monatomic gas. So we have 4 moles of it, N equals 4.0. Temperature is 293 Kelvin at 1 atmosphere pressure. And it says that Q, it absorbs 1830 joules of heat, so that's Q equals plus 1830 joules. Change in temperature is plus 45 Celsius degrees. And the question for part A is asking how much work is involved in this process. So we're looking to solve for W. The first law of thermodynamics says delta U equals Q plus W. So we solve that for W. W equals delta U minus Q. Delta U is 3/2 nR delta T, and then we're subtracting Q. So we plug in the numbers from there. 3/2 times 4 moles times R times 45 Celsius degrees minus Q, which is 1830 joules. And we get work of 414 joules. Part B, because work is positive, we say that the volume decreases. Part C has us changing to a change in temperature of only 15 Celsius degrees. So when we plug in the numbers, work becomes negative 1082 joules. And since work is negative, that means that the volume increases. Next, we'll go to number 33. Okay, so for number 33, it says find the internal energy of 2 moles of argon, which is monatomic gas. So 2 moles, 273 Kelvin, pressure at 1 atmosphere. And U equals 3/2 nRT. So we plug that in, 3/2 times 2 moles times 8.314 times 273, and we get the internal energy of 6809 joules. Now the next part of the question says, if gas pressure and volume both double, what's the change in internal energy? So what we can do, if we want to know change in internal energy, you use delta U equals 3/2 nR delta T. Well, we need to figure out what happens to delta T. So here's something we can do, and let's look at the right-hand side of the page right here. Starting from PV equals nRT, and again, we want to see what we can, we're basically looking to figure out what is the delta T, what is the change in temperature. So let's go back to PV equals nRT, the ideal gas law, and this is a technique we taught back in the previous chapter. You arrange PV equals nRT, get all the variables on one side and the constants on the other, so we get PV over T equals constant, which means that P1 V1 over T1 equals P0 V0 over T0. Now, again, the goal here is to solve for the change in temperature. So let's figure out what the final temperature is in relation to the initial temperature. So solving this equation for T1, algebraically we get this. T1 equals the ratio of the pressures times the ratio of the volumes times the original temperature. Now the question said that the pressure is doubled. So the ratio of P1 over P0 is 2, because P1 is twice P0. The question also said that volume is doubled, so V1 over V0 is a factor of 2. So this becomes final temperature is 2 times T0. Which means final temperature is 4 times T0. What we can then do when we solve for delta T, remember delta T, change in temperature, is always final minus initial. So by definition, delta T we can say is T1 minus T0. Now make this substitution, because up here we said that T1 is 4 times T0. So in place of T1, call that, substitute 4 times T0. So now we have delta T is 4 times T0 minus T0, which means that delta T is 3 times T0. That's the expression we've been looking for on this right-hand side. So now let's plug it in over here. In place of delta U equals 3 halves NR delta T, now we can say delta U is 3 halves NR 3 times T0. Let's move that 3 over to the side, factor that out to the side, and now we have it's 3 times 3 halves NR T0. But that is exactly, if you go back to the top of the page, what this was, 3 halves NR times the original T. The original internal energy, thermal energy, was 6809 joules. So now we move down the page. So 3 times that original internal energy, 3 times 6809 joules, and we get a change in internal energy of 20,430 joules. Let's do one more on this video, number 38. So for 38, a balloon contains 0.30 moles of helium, constant temperature of 300 Kelvin, and its volume expands to 5 times. And the question is asking for an isothermal expansion. What is the work done? Okay, so what we know is right here, N equals 0.30 moles, temperature is constant, 300 Kelvin, final volume equals 5 times original volume, or initial volume. What is the work? Well, since it's isothermal, we go to the isothermal work equation. Work equals nRT times the natural logarithm of V initial over V final. Plug in all the numbers. N is 0.3. We have R, 8.314. Temperature is 300 Kelvin. Natural logarithm of initial over final. Now final is 5 times V initial. So we have in these parentheses V initial over 5 times V initial. The V initials, they divide out, and we're left with the natural logarithm of 1/5. So when you plug in those numbers, the fact that you're taking the natural logarithm of this fraction is what will make the whole thing negative, and we get W equals negative 1204 joules. Since it's negative, that means work is done by the gas. And, I'm sorry, the question is asking what is the work done by the gas. Since it's negative, that means the work done by the gas is 1204 joules.